Yeah, so I'm a professor here at UW Bothell in the School of STEM Physical Sciences Division. My interest is in modeling the Earth climate system, especially at very high spatial resolution. And in doing that, there's two motivations. One is to understand the basic science of the climate system, but the other is also to produce information that can help people plan for climate change, future climate change, to take adaptive strategies to try to reduce the impacts on human and natural systems from future climate change. So what I'm going to talk about here is two branches of my work that have been done in collaboration with colleagues who are bringing this information into actual actions to prepare for climate change. And both of these will focus on flood risk and managing flood risk and the changes in the flood profile, flooding profile in urban areas in particular toward the future. The first one is based here in the Puget Sound region, and the second is in Southeast China in the Pearl River Delta. To talk a little bit about flood risk and how climate change affects flood risk, I start with this little schematic of the Puget Sound region. So here we see the outer coast here with the inland water represent Puget Sound or an estuary, and then a river that goes up into the mountains. The most direct and easily predictable effect of climate change on flood risk in a system like this is that warmer temperatures reduce the amount of snowpack in the mountains, which means that when it rains, it comes directly into the rivers immediately. When you have cooler temperatures, most or some larger fraction of the precipitation falls as snow and stays in the mountains and melts very slowly, trickling in rather than coming in a big rush with the precipitation. So that's it's a direct and it's already observable, the effects of warmer temperatures on stream flow in rivers in our region. The next effect, cascading down geographically, is heavy precipitation. So particularly in urban areas, our flooding is due immediately to direct precipitation falling on the ground around us and inundating the surface rather than overflowing rivers. And so changes in the type of rainfall that we get in an urban area, you could change the flood risk profile there. When we look at urban areas too, I mean, often a city will be flooded directly by a river. Maybe here or in Portland, say, rivers aren't flooding the cities directly so often, but if the river level goes up higher as a sort of a standard situation, then when you do have a heavy precipitation event, there's nowhere for that water to go. So even without a change in heavy precipitation, with rising river levels, we're more vulnerable to the effects of flooding from a heavy local rainfall event. The other things that can happen is there could be changes in the storms themselves. So often with climate change, we assume everything is the same as before, it's just warmer and what the direct effects of temperature are. But the weather patterns themselves could change, and we could have different kinds of storms hitting our coast. And that could change where the storms hit the coast, and could affect the angle that they hit the coast, which, if you know from our topography, sometimes it rains in Everett, and sometimes it rains in Seattle, and sometimes it rains somewhere else. And so just very small changes in the structure of a storm can affect where the rainfall reaches the ground. And the last thing would be global sea level rise. And that's actually also the most certain are kind of bookending our system. Warmer temperatures increasing snowpack and warmer temperatures increasing sea levels, which many parts of the world are worried about direct inundation from rising sea levels, but in places that are not directly vulnerable to being inundated by rising sea levels, there's still the pressure that the ocean places on moving water out of the urban environment and into the ocean. With storm drains eventually have to go into the ocean. If you raise sea level, then it's harder to get the water out and into the ocean. So the idea is to try to understand how all of these components of the climate system interact under climate change and how they affect flood risk profile, and then provide that information in a way that a city can actually plan for future climate change how they manage flood risk through infrastructure, through regulation, through urban design, through development patterns, et cetera. With flood risk, it's relatively more of an engineering problem than, say, something like the effects of extreme temperatures, where you have more cultural, social effects and how people's behavior affects their risk. So I'm starting work now, moving more toward looking at effects of heat on populations. I probably won't talk about that if I'm talking slower. So I tend to plan a 15-minute talk and then still be on my title slide 10 minutes into the slide. So we'll see how far I go. So flood risk is from my point of view, trying to get this information into action. It's relatively straightforward because there's a whole infrastructure, the Army Corps of Engineers, the people who manage the like Seattle Public Utilities that manage the sewer systems, et cetera, right? And they're all engineers and they know how to use information and data. So, plugging that in is pretty direct. Other problems, epidemiology and disease, public health, you have a much more varied and larger set of people. Being here where I am, in terms of my research, this has been a nice way for me to do this kind of what I call actionable science, and I'm trying to expand that ever more, with larger collaborations. But to do something like that has the public health aspects in it really requires a very large collaborative effort. So my focus is really on urban stormwater here. Talk about that. So, usually when people talk about climate change and the risk of extreme events or something, this information comes from what are called global climate models. These are simulations of the future climate under various scenarios of future greenhouse gas emissions. And they're, they run at the global scale. And you can see that this map is made up of little squares, and information is presented from these models at the scale of those little squares. So, Western Washington is one number and Eastern Washington is another number. But, we know very well here that flood risk in Everett is very different from Seattle, never mind over in Yakima or something, right? So in order for this information to actually be useful to people, we have to provide the information at the scale that they need the information, and that incorporates all of the climate system drivers like snowpack, mountains, Puget Sound Inlet that actually control their exposure to climate change. But from these global models, we do get the main sort of large scale forcing on the climate system. And we do know that with warmer temperatures, there's a modest increase in total rainfall precipitation over a year. So in our part of the world, about a 10% increase in total precipitation. That might sound like a big number, but our precipitation varies by like a factor of 2 from one year to the other. So 10% gets kind of buried in the noise. If you've lived here very long, there are some years with this huge amount of rainfall, and some with this very little. But in terms of the rainiest day of the year, so if you look at the rainiest day of the year now and the rainiest day of the year in the future, that actually increases by more than the average. So this is an interesting situation where the average day, or, on average, we don't see a lot more total rainfall over the year, but this rainfall is coming, in more intense bursts, shorter time scale, and and focused more geographically. A heavy precipitation event is usually, very short, very localized, and so to really understand these, you need that kind of detailed information. So, it's well known that there's this risk of slightly larger total rainfall, but a shift also to more extreme events in the future climate. And so, and another issue in our part of the world is that these intense rainfall events come from what are called atmospheric rivers or Pineapple Express events. This is a picture of one on the left. which this red arrow is showing sort of this fire hose of water vapor being directed across the warm Pacific Ocean to our coast. And when it hits the mountains, that air lifts up over the mountains and cools and dumps a huge amount of rain and snow. They're very desirable in some ways because they're kind of drought busters, particularly in California. They rely on these to actually fill reservoirs, and here as well. So when we get an atmospheric river, skiing is good. The hydropower is doing well, but they can cause a lot of flooding in the rivers and the urban area. So this picture here that I started out with, that's an atmospheric river event in, I can't remember which one this is, but it's this is I-5 south of Seattle somewhere. The Chehalis River, I think, comes down through here, and that's overflooding the highway and the industrial area there. And so these are highly damaged. All of the highly damaging floods in our area really are from these kinds of events. So the studies we've done show that these become more intense under future scenarios of climate change. When I talk about future scenarios of climate change, usually I'll be talking about like worst case scenario situations. Very unlikely that the worst case scenario. We have always, since the beginning of studying climate change, used this worst case scenario as the sort of planning horizon. And despite the fact that we haven't gotten to the targets of, say, the Paris Agreement, we have done enough work in reducing greenhouse gas emissions that the worst case scenario is probably now is now perceived to be less and less likely. So the 5-degree warming by the end of the century is probably not going to happen, but we still can't rule out, say, 3 degrees of warming as we try for 2, right? So over my lifetime of working in this field, we've gone from 5 and worse degrees of warming as being something we had to plan for, but also the possibility that we could all be wrong and nothing will happen. So now really narrowing that down to high degree of certainty between 1.5 and, say, 3 or 4 degrees of warming. Here I'll be always talking about kind of the worst case scenario. And that's a reasonable planning benchmark for people to use. If you plan for the worst case scenario, it covers a lot of uncertainty and gives you space for other impacts. So here, zooming in on Seattle, this is just a chart of the 10 wettest days in Seattle historically. And as you can see, of the 5 heaviest events, they've all occurred in the last about 20 years. This 5-inch day kind of stands head and shoulders among the rest of it. You would have thought that 3 inches of rain in a day was like the top where we would max out. And then we've had quite a few events recently. This one 1959 event was more than 3, but hitting 5 inches. That's sort of the rainfall equivalent of the heat wave last summer, where we got 108, right? So getting 5 inches of rain just call it a record-shattering event. So so there's absolute reason to be concerned that these sorts of events could continue to happen. So we have this high certainty of reduced snowpack and the influences that will have because of warmer temperatures, and this very strong suggestion of changes in rainfall patterns coming down. And observationally, this is evident already in flood statistics. This is the Chehalis River, so that's near where I showed that flood in the first slide, right? And this is stream flow, volume, and years on the right. And you can see, there are plenty of low years. Not every year is a flood, and we see highs and lows. But there's these recent events that are record-breaking events that are now what you can sort of think of is that the climate change or the warming climate has made it possible for certain kinds of rainfall events to occur. That doesn't mean that they will happen, but they're now energetically possible within the climate system. So we're definitely beginning to see these sorts of things, and that's a reason for concern. So we look in at Seattle. What do we do when it rains? We have a stormwater system, and ideally, the stormwater system, removes the water from the places it could do damage, like streets, people's houses, and such. But you can see in these pictures, it doesn't necessarily always work, right? And so these stormwater systems are overwhelmed. Unfortunately, in King County, we have a very old-fashioned stormwater system. It's called a combined sewer system. So here's a house with these lines here showing, so it's not raining, it's a nice sunny day, right? And the sewer system takes stuff from, people's sanitary sewer from the bathroom in the laundry room and puts it into the sewer system, and it goes to the treatment plant. And that sewer is treated before it's put into the environment. But you can see that some of its roof drains and the storm drains go into the same sewer system. So when it rains really hard and the sewer system gets overwhelmed, it's not just the stormwater that runs into the environment untreated. When the sewer system gets overwhelmed, you have I don't know why they call it sanitary, because it's unsanitary, right? The nasty stuff from the laundry room and the bathroom gets mixed with the stormwater, and all of that overflows into the environment. So there are these overflow pipes that go into Lake Washington, and they dump untreated sewer into the lake, which include, and in addition to any disease they may carry, they also carry nutrients which create harmful algal blooms in the environment. It reduces the oxygen content in the water and kills fish. So the county has been operating to upgrade the whole sewer system, to create a separated sewer system, to create bigger pipes, basically to manage the water, culverts that go under streets. So all of these things that you see failing here, right? This is lack of culverts. This is combined sewer nut, right? And in doing this, they want to make sure that this thing is designed not for the last 50 years, but for the next 50 years, right? And so so some of the work that we've done in modeling climate. So this is just tended to show the modeling change. So I showed you that picture early on of the sort of chunky world that is sort of the standard information about climate change. This is a chunky global climate model world. We've been running and using now the HIAC system at UW. We have funding now to run there, running this high resolution model that actually can zoom in with great deal of detail on the specific issues creating precipitation in our region. And then this can be put into additional models to see the river flow and to do the hydrology of urban flooding. And that information can all then be used for planning purposes. How big, this seems rather boring, right? How big should the culvert be under this street? How big should the sewer pipe be over here? Right? But that's the kind of decisions that need to be made in order to manage the situation we find ourselves in with flood risk and climate change. So here's this. I think this is actually the event that is the flood in that first picture. So the coastal gale of 2007. So it's an atmospheric river event. It's called Pineapple Express because they start here in Hawaii. I come across carrying subtropical, moist, warm air and lots of rain. Often these things will come, early winter, late fall. Sometimes there'll be snow on the ground in some places, and then these things are very warm and wet. They'll come in, not only will it rain, but it'll melt snow that's already present. And so with warming temperatures, the ability to melt that snow becomes greater, and all the the flooding from both melting snow and so this is just trying to simulate that same event. So one of the things that we do is we go back and we look at what history looks like and simulate history so that we can replicate what's happened in the past, and people can design to a 500-year standard. Okay? Maybe a school is a 100-year standard. Your housing 100-year standard. You don't want to build a house somewhere where it's going to flood more than once every 100 years, or where more than 1% of the houses are going to flood in any given year. This is another tool created through the Climate Impacts Group. This is showing a river coming through Everett, and this is a typical historic flood that might happen once every 10 years. So a 10% chance of happening in any given year, or a 10-year event. Here's a bridge here, Spencer Island Bridge. So you can see typical current flood, and then you can simulate the future. So this map here shows the inundation, filling the valley walls. It's getting up closer to the bridge. That's for the 2040s, and then 2080s. This is a typical flood for the 2080s, inundating the bridge, and really filling that whole floodplain, valley wall to valley wall. So a combination of sort of the kind of tools that engineers would use to actually put into their models, plus visualizations. You can, if you live in there, you could go find your house and see what your your flood profile would be. So this information is used by Army Corps of Engineers, by, as I say, all these different cities to help plan not only infrastructure, but land use and these other things in order to prepare for future flood risk. So I'll just quickly say that we've been doing a very similar sort of work, set with a collaborator in China, in Zhuhai, China, which is on the Pearl River Delta near Macau, to do sort of similar work that they're doing there. But again, urban flooding, this is Macau, running the same model there for Southeast China. This kind of simulation we can do. This is a typhoon, simulation of a typhoon. So we can simulate these sort of events for the next 100 years, under multiple climate scenarios, and see what does this event look like in 2100. The interesting thing in China is that they have decided to take a whole-scale new approach to urban design in their cities in order to better manage flood risk, called sponge city design, where they are trying to be much more organic in how they manage floodwaters by using more green space, having underground storage for water. Then linked into that and running this model, and my collaborator there is an urban design engineer working with the cities there. So I worked with Zhuhai and the capital of the Hunan province, Changsha, to work on that. Help. Actually, so I go and I talk in English and I get translated into Chinese, and it's all a little bit confusing. But they've made some good progress. Unfortunately, that's all been sort of on hold now because of COVID and politics and everything, and so hopefully that will soon be able to get back online. But they're making significant advantage of the data in terms of engineering the flood risk in some of these cities. So adjusting ground elevation, putting better stormwater management systems, as well as all this sort of green development. Anyway, I shall stop there. What I'm trying to do is really push the climate science beyond just, so 20% increase in extreme precipitation in the future, to city of Zhuhai. These are the neighborhoods where, and these are the events, and these are the time of year where future climate change is going to create flood risk problems that you're not able to manage currently, and where you should focus your investment. That's sort of my goal.
Great, thank you so much. So interesting. Does anybody have any questions right off the bat? Jay.
Oh, thank you very much for your presentation. That is awesome. Are we expecting more heat waves in the future in this area?
So the answer is yes, in part, but a lot of it depends, of course, on the where we end up in this trajectory of greenhouse gas emissions. I would say at this point, the effects of climate change that are emerging now, most obviously, are loss of snowpack and changing the timing of flow in our rivers when snow water melts. That's having a big impact on where we are. Temperatures have risen about 1.5 or 2 degrees Fahrenheit, about 1 degree Celsius or so, and that's important, but it's still small compared to the variation from year to year or day to day. But as we go forward now, these will be, I would say at this point, climate change is changing the character of events that we already have. And the risk in the future is that climate change will be creating different kinds of events from what we have now. Okay, so the heat event last summer without climate change would probably have been very similar, but it would have been 106 degrees instead of 108 degrees, right? The big risk is that we get these sort of record-shattering events coming in the future. And that's where a lot of the concern is, that you get more energy in the climate system, you can evaporate more water into the atmosphere. Can we create kinds of events that just are way outside the envelope that we've been adapted to? And so when people say keeping climate change to 2 degrees or 1.5 degrees, it's trying to keep it out of that range of these sort of record-shattering events that sort of change the nature of the storms themselves. So I would say, our hope is that, we stay within the realm of climate warms by a degree or two and heat waves are a degree or two warmer, which is not good and stresses all sorts of parts of our system, but it's something that we know how to to address, at least in the wealthy parts of the world. That
Okay.
makes sense?
Yeah. Yes. Thank you.
Somewhere between panic and plan.
Panic. I have one question. I haven't seen the term sponge city before. Is that similar to a rain garden, or does that also incorporate the
So
stormwater?
rain gardens are part of what you do in a sponge city. Actually, the best example locally in Seattle, I don't know if you, but in Seattle, in the Madison Park neighborhood, there's a park that they've put that the whole park is kind of angled downward, and there's a big storm drain in the middle of it. And they planted this whole green area where floodwaters traditionally have collected. There was a woman who was actually drowned in her house in 10 years ago. So they built this in order to manage that kind of flood risk. So it's think rain garden, but times 100. Okay, so all of those sorts of things. Cities are actually putting tanks underground to store water. So, the normal healthy way the ecosystems work, right? You've got soil and leaf litter and trees and all this stuff, and it rains hard, and it just gets absorbed into the system. When you engineer and put impermeable concrete down, the water has to go somewhere,
right,
and stay there.
Great. Well, thank you very much. Does anybody else have a last minute question?
I have just one really quick question. I'm curious about how the use of HIAC has changed your research.
Yeah, so we've done a large number of climate simulations. We got some money. A colleague of mine who's been running the model got money through Amazon Catalyst to run some of these on Amazon system, whatever they call it, AWS. And then we had some time through collaboration with the Department of the College of the Environment to do that, but it's all very awkward. And to be able to run these, AWS is not really ideal because you can only run one node. I don't know how technical you want to be, but HIAC is just so much better a system for doing this kind of work. So we're looking forward to really expanding the kind of simulations we can do.
Thank you.
All right, well, with that, we will conclude our Husky Highlights seminar today. Thank you very much.